All right, so again, today we are going to walk through the TensorFlow, and it's a very important topic for all of us. And today is going to be probably a far more involving class, as in it's going to require a bit more of background on maths. So what we are going to do is, we are going to go with the basics of maths. We will assume that none of us have any foundation in maths. So we will try to be more explanatory, and I would expect that all of you to ask questions even if it looks like really, really basic, okay? Because those basic questions are something because of which we don't generally proceed. All right, so we're going to maybe go into really basics of maths even to as we go ahead today, because there are a couple of terms that might confuse you, okay? Though it's not mandatory to understand maths, but it'll make you extremely comfortable with the entire tooling. So is everybody okay with the if we go with bit of maths? All right, we will so if needed, we will explain differential calculus a bit, and also um, we will even talk about what does it mean by uh, dy by dx or differential in first place. Okay, because the things that we are going to learn are really fundamental, and those are the fundamental that have been changed with TensorFlow or with new tooling. Those are the fundamentals that have been addressed with these new tools. Okay, so it is important to revisit the fundamentals, and that's what we are going to do. But we will move forward, and then whenever required, we will walk backwards to explain individual concept. Okay, so please feel free to ask questions, any questions. Okay, at any, because this is a topic where um, uh, where I have a big fear that you might lose interest. Okay, so I would try my best to make it more interesting. So the only way we can figure out how to make it interesting is based on your feedback, your questions. Okay, because it's okay to expand it a more, because what I understand is even those people who are really good with maths, they will learn a lot today. They will learn a lot today. Okay, and we will also focus on Jupyter scripts. Thank you, Binta. And what we will do is we will focus on the code and walk backwards to explain individual bit, and that's how we will learn. All right. So so far, what we did last time is we learned about the end-to-end project. That is the classic way of doing machine learning project. And the part that changes with these new tools like deep learning, machine learning, deep learning, TensorFlow, and um, the various concepts of deep learning. The only difference from that approach to this approach is that deep learning introduces more algorithms in the last step. You remember the last step where we put the decision tree, we put the other uh, algorithms, right? When you compared all of them. So that is the point where deep learning introduces more algorithms and help you giving far better results. Okay, so this is where the deep learning fits into the entire end-to-end project. So now coming back to the TensorFlow part. So here we have let's get started. All right, so far we have talked about basics of TensorFlow. We all installed and got started, right? Is everybody up and running with the Jupyter? So are you able to locate your folder? You have checked out this code? Yes? Is everybody able to look at this deep learning folder, click on TensorFlow? Okay, so before we start, go to the terminal. You click on new terminal and a terminal will open like this. Okay, and here as let me just close it. Okay, so when you go into Jupyter after my lab, CloudxLab, my lab. Okay, so here if you click on Jupyter, this is the kind of folder that you're going to get. Here you say new terminal, open Jupyter, open the terminal, go to ML folder. If you have not checked out yet, do the git clone and check out. Okay, so we are saying cdml and we are saying git pull is going to bring the new version of the content. All right, everybody has updated their repository ML. Balaji, Bintao, James, Ross, and Shiva. Done? Great, great. All right, all right, wonderful. So let's now go back to here. Okay, is it giving an error? Git pull is giving an error. If git pull is giving error, let's say you modified something and there is a change on the server side at the same time, so it'll give an error that there is a conflict. So there are two choices. One is you can simply say git checkout for that particular file which is conflicting. What does git checkout do is it overrides your local changes with the one that is based on the repository, and then you can do git pull. Okay. All right. Is anybody stuck? Do you need help? Uh, Okay. All right. Great. Great. So I'm hoping that you would have located by now the ML folder. Okay. I think it'll be okay here. So this ML folder for me is here in my at the top level. It should be the same location for you also. And there you will have the deep learning folder. Click on TensorFlow dot. Okay. Yes. Is everybody able to locate? It should be modified around 8 hours ago, or maybe earlier. Yes. All set. So this is where we are starting. Okay. Balaji, Vintao, James, Ross, and Shiva. All set. Okay. All right. One more thing I came to know about some new things in Jupyter that actually, if you want to say time something, find out how much time something is taking, put percentage time in the beginning. Okay, that shows you the time consumed. Okay, that shows you how much time is consumed. You see that? CPU time, system time, and total time is this much. Now, if you want to find out about anything, let's say you are importing TensorFlow here, okay, and you want to find out what does it mean by TensorFlow actually. You want to find out its manual. So put a question mark after it and press Shift Enter. So you see here there is this pop-up that has come up. Okay, it shows the documentation. Okay, in the similar way, you can further, let's say numpy, np, and I say not here. I will say, let's say below this one. To add something below a particular cell, you can uh, escape and say B. Okay, escape and say B, and you could, let's say I want to find out about matplotlib. Question mark, shift enter. Okay, so you can see that you have a manual of matplotlib. Good. Okay, great Ross, great Ross. So Ross got CUDA and TensorFlow, meaning the GPU. And okay, so how many GBs is it? Is it 4 GB or 8 GB? 6 GB. Okay, wonderful, wonderful. 6 GB is good. 6 GB is great. Okay, yeah. All right, great. Now, all right, so everybody is up and running with this. So let's move on now. All right. So one thing that we missed last time was discussing something about lazy evaluation, right? So for Shiva, it's throwing git pull is throwing error. Okay. So what kind of error is it, Shiva? Do you want to show the screen? We'll just take a look at it and we'll guide you so that this is the beginning part that we don't want to miss at all. Okay. So please feel free to share your screen so that we could help you. Okay, so since you have already, there are some local changes in machine learning end-to-end project. Either you can, are those changes something that you want to keep, or you
Uh,
are okay to let go of those?
I think I can let go of it.
Okay, so say you say git checkout space, and just select the entire path, machine learning slash end-to-end project bootcamp.ipynb. Um, yeah, 3 lines above your cursor.
This one, right?
Or you can just say git checkout star. Thank you, James. You could also say git checkout star or git checkout dot. Okay. Just say git checkout space dot or star. Yeah. Uh, on either of them. Okay. Yes. So do git checkout dot. Git checkout dot. Yeah. Okay. Now you can say git pull. All right, so you got, now it is working. All right, good, good. So, so that's how, if anybody else is facing the similar problem, you can actually solve it the same way. Great, great. All right. So one of the examples that I would like to give you is a lazy evaluation example. Okay. Before we go into graph and try to understand the more about graphs in. So imagine that there is a restaurant, and in the restaurant there is people go and place orders. Okay. So let's say there are two persons, and first person orders that uh, cheeseburger, soup, and a plate of noodles, right? The second person orders soup and a plate of noodles, and so you can see that the waiter has silently waited and taken all the orders. Now uh, so now here the waiter has waited patiently and then basically consolidated orders. Okay. Now again here, as this point of time, the chef will be able to optimize, and will be because of clubbing of the orders together. So there are multiple orders in a single, multiple items in a single order, so a single order being placed by the user, and the and the and the waiter is able to optimize and group the items together because of patiently waiting. And only when the user says execute, only then the waiter is going ahead and placing the order, right? So this is lazy way of doing it. This is lazy way of doing it. Okay. So if you think about the instant evaluation, the opposite of the lazy, the way most of the programming happens today, most of the usual programming languages or frameworks are non-lazy. Okay, they are instant. Imagine there is a waiter who is really fast and is on the roller skates. So the moment you utter something, like somebody said cheeseburger, so he just goes to the kitchen, gets the cheeseburger uh, first, and then listens to anything else. Okay, so this is really fast waiter. So and the soup, let's say you had to order burger and the soup, so he'll first bring the burger and then bring the soup. Okay, now which one do you prefer, the instant waiter or the lazy waiter? Quickly. So there are two waiters. First one is waiting for somebody, all the orders, all the orders from a table, and then once you say that okay, I'm done with placing orders, now you can get my food. So this is the lazy way. And then there is a really fast instant waiter. You utter a particular item and he just goes to the kitchen, rushes to the kitchen and gets it back. Okay. Okay. So for your two parts like burger and soup, he made two trips to the kitchen. He made two trips to the kitchen. Okay. Instead, he could have actually gotten both the things in a single shot. So he could have saved one trip till the kitchen, right? So in this case, in most of the programming cases, the lazy evaluation is generally a better idea. Lazy evaluation is a better idea. Okay, and this is where TensorFlow comes into play, or TensorFlow, Spark, or there are many lazy frameworks as of today in which you write everything upfront, right? As in you give your orders, and then in the end you say execute. Okay, So pig was one of that, Apache pig, the pig in pig Latin. And Spark is similar, and similar is the case of TensorFlow. Okay, so what basically, instead of instantaneously executing, you in case of TensorFlow, what you do is you create the list of orders, and that's what we call the graph. Okay, so what are the things that we are saving here? One, in case of here, what are the things that we are saving? One, the waiter is not making multiple trips till the kitchen, correct? Which means that, let's say there is a programming. I'll come back to this one. This is a very important part, because we kind of fail to understand this part. So one is the waiter is making multiple trips till the kitchen, right? For each table, the waiter would make multiple trips. Instead of that, if the waiter is lazy, they'll be able to get the food quickly. The second part is the waiter would be able to optimize, or chef will be able to optimize and club multiple orders together. Okay, so similarly the case with say Spark and other frameworks. So if you have uh, gotten the idea by now, like I'll talk about this one. Okay, so on the left hand side, say we have libraries like say NumPy. Okay, NumPy, or say okay, scikit-learn and NumPy. Okay, so under the hood, these libraries are implemented in say C. Okay, so these libraries are implemented in C or C++ because that one is faster. And here is the Python side, correct? So every time we interact with something, we create np.dataframe, or we convert something, our objects are being translated to the C side, correct? And back and forth, right? So here you see that if for everything, if the evaluation is happening in a single shot, there are multiple trips. Okay, so if you imagine that this side is the kitchen and this side is the waiter, your table, then this transmission is happening multiple times. Okay, and every time we have the similar scenario, we basically end up doing many back and forth. Now, first is that there are multiple operations that could be clubbed together. Second is the transport cost. Transport cost, as in there is no network transfer though in this case, but in some case there could be network transfer. So this cost is basically translating the Python object into something understood by C. So this is basically what is optimized by these new frameworks. All right. So great. Let me just skip this part. Okay. Now, so TensorFlow, this we have already talked about. It's for numerical computation. It's fine-tuned for large-scale machine learning. Okay, it was done as part of Google and is being used everywhere around the world. Okay, before TensorFlow, there were other libraries for doing the same thing. The other advantage of TensorFlow, other than the lazy computation, is that actually TensorFlow is written in C++, which is extremely fast, but it provides the bindings in R, in Python, and I'm not sure if they have opened up for more languages, but they will open for more languages, right? So the when you are communicating with the say TensorFlow from Python, there would be object translations in between, and that is one thing that is saved by creating graphs. The other thing that is saved by creating graphs is that it is able to optimize, And third part is that it is able to execute your graph onto, it is internally very parallel, and it is able to execute your work parallelly onto multiple CPUs or GPU. Okay, that's why you always design your code as if you are creating a big graph, right? So here is an example. So here is a non-lazy way of doing it. Here is the non-lazy way of doing it. So if you go into TensorFlow, the first line that you see is here, x equals 1 and y equals 2. This was non-lazy. We quickly assigned 1 to x and 2 to y, and then we executed the function. Okay, so you can see that the value of f is 6. Great. So it did not wait. This got evaluated instantaneously, this got evaluated instantaneously, and so on. And this whole expression got evaluated the moment you pressed enter here. Okay. So, basically, this is the traditional way of doing it. In case of TensorFlow, we create the graph. We create the graph, and the graph is made up of operations. The leaf nodes are either variables, constant, or there are few more data types. We'll talk about them soon. Okay, and then every node that you see is an operation. Okay, so here this expression is represented like this. So we have y plus 2, right? So this value is essentially y plus 2, because okay, and then this side is x square, and then x square into y is this value, and this value is x square into y plus y plus 2. Okay. All right. So TensorFlow runs this graph efficiently using optimized C++ code. And internally, the graph could be broken into multiple chunks internally and can be executed parallelly using multiple GPUs. So this portion is, let's say, hypothetically, this portion is being executed like x square is being x square into y is being executed by GPU, and y plus 2 is being executed by another one. Okay, so you can see that the values of y and others could be executed twice in such cases. We'll talk about this very soon. And then the result of both of the GPU is combined together. Okay, so if there are two GPUs, let's say this portion took 1 millisecond, this portion took 1.5 milliseconds, and let's say this is taking half milliseconds. Okay, so the overall time would be, this is 1, this is 1.5, and this is half. So it'll be max of 2, which is 1.5, and plus 0.5, which is 2. So overall time taken was 2 seconds instead of 3 seconds, 3 milliseconds. Okay. So I hope that is clear to you. So basically these two parts will become parallel, and that's how the computation will become significantly faster. Okay, now TensorFlow also supports distributed computing. We will cover distributed computing in this course after this. So instead of using the instead of using the yarn instead of using yarn or say Spark or Hadoop or any other distributed framework, TensorFlow has come up with its own distributed framework, and we will cover that in this course. Okay, now a question from Vidya is, do I have to have a graph picture in mind first and then write up the code to follow that graph as a guide and work out of the expected results? So actually the good news is that we in general have the graph picture in mind, and when we are expressing, we are essentially expressing that graph. Okay, so it comes quite naturally to us to write something as a graph. Okay, And it's just so graph picture is anyway there in our minds when we are expressing anything. Okay, and we basically express in our most natural way, the way we have expressed here, the way we have expressed in this expression, right? It's essentially a graph. Okay, so graph picture is there already, so we don't have to worry about that. Just that if we need to visualize the graph, we can take a look at, say, TensorBoard. We will show you today that how to look at TensorBoard and take a look at the graph. Okay, and yeah, so I think visualization later could help you figure out what is wrong with the graph, what is wrong with expression. All right, great. So it can work. Okay, so it can work on multiple computers and so on, and it can run on all kind of devices. So since it's not always possible to start writing from the scratch and code every algorithm, so we generally use a high level language. So TensorFlow, even though we are going to go into detail more and more, in most of the practical scenario, we will be relying on the library like TFLearn. Okay, just like we used scikit-learn all throughout, even though we used basic expressions from time to time, basic Python from time to time, in the same way we're going to use TensorFlow as well as TFLearn. In case of the real projects, you will generally end up using Keras or say TFLearn instead of coding entire thing by yourself. Okay, and generally the computation, when it becomes uh, more and more lazy, it is not something we have coded generally. So it looks little awkward for many programmers to look at the lazy way of computation. Okay, so that's why that's why coding for TensorFlow raw could be much time consuming in case of production. So you would generally end up with using either tflearn or keras. So those will be the high level libraries. And okay, all right. So the Python API offers a lot of flexibility to create all kinds of computations, including any neural network architecture. Okay, so highlight the C++. It also TensorFlow also has a C++ API which you can use. TensorBoard is something we are going to talk about. It is a way of you know visualizing your computation, like how does your graph looks like, how much CPU being consumed in what areas of code, and so on. So it is quite helpful. So we will try to give the demo of this part. Okay, it's an open source, and it is going to be open source. So it is completely okay to use it for production, for education, or for any experimentation for personal use. So it's completely okay, and it's open source, and you can take a look at any piece of code at any point of time. So there are many deep learning libraries other than TensorFlow. The first ones were Caffe and Theanos, but as of today, everybody has moved to TensorFlow. Okay, so so far out of all the libraries, probably TensorFlow is the one where it is going to be long term. It's going to, uh, it's going to be useful in a longer term. Okay. Now, now let's create our first graph and start and run it in a session. Okay. All right. So this is what we had already done. So I'm just going to go super fast on this. So here was our Okay, these are the functions that we would require. So we'll just execute this without understanding this part. Okay, so these are for drawing the, I mean, save the figure and things like that. So that will be useful later. So for now, we can just skip that. We can just say Shift Enter and move ahead. Okay, now, all right. So this is where this is how we create a graph. First of all, we are resetting the graph. Even if we don't reset, it won't be a problem. Okay, just that we have created a function here that does resetting of graph. Okay, that does the resetting of graph. All right, either you can call that function directly, okay, or you can just completely skip it. Now here we are defining a variable called x. Its value is 3, and we are giving it a name called x. Okay, similarly we have a variable y. Okay, we have a variable y whose value we this is the TensorFlow name, this is the Python name, and this is the name with which it will refer this variable internally. And here we are expressing it like this. Okay, so you can see that f is not really a normal value. If you say f, it says it's an object, it's a tensor object. Okay, it's a tensor object. Now how do I execute it? We basically, the way we execute f is, first we create a session, initialize variables, we initialized x and y, and we we run the session. Okay, then we run the session, meaning hereby we are saying that run f. So after initializing x and y, we are running f, and then we are printing results. A question from Bintao is, how many libraries will be covered in our deep learning course? We will mostly focus on TensorFlow. Okay, if needed, we will switch between the Keras and TFLearn, but we'll give you an overview on how to use both of them. Probably one example of Keras and one example of TFLearn. Okay, so that will be good enough for you in this course. So mostly we are going to stay with these three. We are not going to go with, say, Theanos or any other library. All right. And also we will utilize our knowledge of scikit-learn that we have done, and basically we'll compare the two approaches. Okay, one with scikit-learn and one with TensorFlow if needed. Okay, now this is how we execute it. So we initially create a session, initialize x and y, run it, and then print the results, and that's it. Now, a little bit better way is that we create kind of a context with, right? The way we open a file and we keep a handle open. In the same way, here we are saying with this particular session, all this block of code that you see is part of the same session. Okay, so we don't need to necessarily call like the way we were using scss.run. We don't need to do that. We can simply say f.evaluate. Okay, so we don't have to call ses.run. Instead, we could just say x.initializer.run and so on. So this one becomes default, as in this session is what is common here. Okay, so inside this session, we are initializing x, initializing y, and then we are evaluating. Okay, and there we go. Good. So this way it has done the evaluation and we have gotten the output from this. We got the output from this. It is 42. Okay, and the same here. Now there is another better way. A question from Minta is where the session function comes from. The session function that you see here is a part of TensorFlow. We have imported the TensorFlow and given it a name as TF, and we are use this TF is the entry point. This TF is the entry point, just like we say numpy np and we do everything with np. Similarly, the TF is our entry point here. So using TF, we created variable. Using TF, we created variable. And then using TF, we created a session here. Okay, TF as session. So we are saying that for this is the line where we are defining a session. So this session is available by default for these instructions. And then you see that so in these lines we are not using session explicitly, but internally that's what is being used. Okay, so again, for execution we need to define something called a session. Okay, for execution we need to define something called a session. So we define variables, then we defined our expression, then we created a session, and then we ran then initialized the variables, and then we ran it. Okay, this might look like just too much for doing very simple thing, but you will see that there are many advantages of this approach. Okay, all right, so was I able to answer your question, Vinta? The another better way of doing it, the same thing what we did, instead of initializing all the variables ourselves, we could just say TF global variable initializer. Okay, so we're just uh, defining this object, which is the initializer. So we could just simply call init.run to initialize all variables. Because if we had like 10 variables, we won't initialize them manually 10 times. Instead, we'll just say define a global variable initializer and then call that one. Okay, so it initializes all of the variables. Okay, a question from Bintao, how many import functions is with TensorFlow? Okay, important functions are there with TensorFlow. So TensorFlow has quite a few functions. Actually, you should take a look at that. Okay, actually, it'll be hard to remember them. Instead, what we'll do is we will start using it. Okay, and at any point of time, you can take a look at this. Okay, so you could generally. So TensorFlow has a huge number of functions. So you can see, just like we had in NP, all the maths functions here, in the same way we have all kinds of functions at the top level itself. So there are huge number of functions. Okay, so most of the functions are at top level itself instead of going inside. Okay, so you can see logging, log, and linear space, and so on. So most of the NP functions are there as part of TF. Okay, and you can explore more, and we will actually explore more. Okay, so there are quite a few functions that are part of TTF object, or you can say TF module. This is a module which has functions. All right, so we, I hope this is clear to everyone. Okay, so only the second part we have optimized, while the defining the variable remains the same. Okay, okay, so now this is what we talked about, right? So we created the session, initialized the variables, and then evaluated, and then then we closed the session. Instead of that, we use this one, and then we use the global variable initializer. Okay, the summary is that the TensorFlow program basically builds a computational graph. Okay, and that's the construction phase. First we code, then there's a construction phase, and there is a execution phase. So we basically, the construction phase, the graph is built. That's what is happening here. So this part is the construction phase, okay, where we are creating the graph. And then the second phase is the execution phase, this phase where it's being executed. Okay. A question from Binta is, could you have us more example with with in Python? Okay, sure. So with in Python, you should take a look at mm, with open file, right? And open file Python. Okay, I'll show you some examples. So, okay, let's say here we are doing that. And does it say with? Okay, just let me give you a good example. Right, let's take this example here. Okay, so I think this is, yeah, let's take this example here. So it says with open file as out file, we do something, right? And then here we are reading it. Okay, in the same way, okay, so you can see that here, essentially this file is opened in this block and will end as soon as it ends. Okay, in the same way, we could actually write our code here. So this, whatever I run here is going to be in this. Okay, so let me just create a simple text file. Okay, let me just create a text file, and let's just say 1, 2, 3, 4. Okay, and this is my simple text file, right? All right, so with is a very good example. So we'll say with open, what was the name of this file? Simple.txt, okay, as f, okay, print f dot read line, okay, or we can just say not like this. We'll say for line in f, print line, right? So you can see that we are able to print it. All right. Then here the question is, then why are we using with when we are also using f here, unlike in case of TensorFlow? Here, the here we are basically iterating over this. The advantage of using with statement is that at the end of it, as soon as it ends, it is going to automatically close the file. We did not need to close the file by ourselves. So that file closing operation is taken care of by Python so that you don't miss out on closing, because we often forget to release a resource. Okay, so for generally this kind of blocks, we have the with. Wherever we have a context, generally we have this. Similarly, if you are automating your network and you are using things like Fab, so there are many examples of this with. So Fab, the fabric execution, for example, there are many such example where you could define the with kind of a syntax. Okay, all right, so you could actually define context and things like that. All right, so take a look at this. There are many examples. I think file example was more something that you can relate with. Okay, so there are many things that could use with, and you could also define your own functions which can support with. Okay, say network connections with, you can use with the network connections so that the connection closes by itself and so on. Okay, so wherever there is kind of what do you say, session closing kind of thing, we generally use the with. All right, so that was an example of with. All right, the next part is to manage the graphs. Any node that we create is added to the default graph. As of now, we did not define any graph here. Here we did not define any graph at all. So it was actually using a default graph that we can access using tf.defaultGraph. Okay, say for example, here we are defining this, and let's say we say tf.get default graph, right? So you could take a look. So here this is that default graph. Okay, so you could take a look at, so you could see that there is a default graph which does this. Okay, so when you are by default, you are given a graph that you can use. Okay, everything you do is under that default graph. Sometimes you may want to use a separate graph. You may want to have your own kind of graph. Then we can do this by creating a new graph object using a function called graph. Okay, so so you can see that we could say um, okay, we could say tf.graph as default, and then we can use that graph. Okay, so we can simply use say here we are getting the default graph, then we are saying here that create a fresh new graph, and using that graph define this variable. This variable define is part of this graph. Okay, and then okay, so you can see that this graph is not same as default graph. Okay, use reset graph function, define the notebook, because that's the one actually calling the reset graph. You can see tf.reset graph. Okay, so it's not a big function, it just calls this, and by default it also sets the random seed at both the places. Okay, remember our example why were setting the random seed? It's the same reason here, to set so that things become more predictable than random. Okay, all right, you could have a different number for the random seed, it's up to you. Okay, so we can reset the graph using that. All right, now so far, okay, so you can use the reset graph, and there we go. Now, the next part that we were coming to in the last session was the life cycle of a node. Okay, so when we evaluate a node, TensorFlow automatically determines the set of node that it depends on, and it evaluates these nodes first. Okay, so basically, whenever we are doing evaluation, it automatically determines that each node value depends on other node values and then does the computation. Okay, so it does that in that order. So for example, here we have defined w as 3. 3 is a constant. X is w plus 2. So when we are computing x, we'll have to first compute w, right? Then we are saying y equals x plus 5. If we are computing y, it's going to compute x first, w, then x, and then y. Okay. Then here, if it is computing z, question to you is while computing z, will it compute y? While computing z, will it compute y? Yes, no. While computing z, will it compute y? So see, if you take a look at it, the z equals x into 3, y equals x plus 5. So computation of z, does it involve y? Does the computation of z involve y? Correct. It does not, right? It does not. Therefore, while computing z, it would not compute y. While computing y and z, in both the cases, it'll compute x, right? Now, so you can see that when we say y dot evaluation, it'll print 10, and z dot eval, it'll give 15. Okay, just try this. So basically, while we are doing this computation, it is doing the rest of the computation by itself. Okay, while we are saying this. Now, in this code, what you notice is that when we say y dot evaluation, it's going to compute x, right? And then when we say z dot eval, it's going to compute x again. So x will be computed twice. X will be computed twice because we are calling y dot eval and z dot eval. Okay? Do you agree with that? So x will be computed twice here in both cases, right? So this is the visual way of looking at it. Y depends on X depends on W. Similarly, Z depends on X depends on W, and you get the results, right? So here, the preceding code that we did just now is evaluating X and W twice, okay? And because when we are running them individually, what's happening is it starts the whole evaluation again, right? To make it run in a single shot, okay, we can actually run y and z in a single way. Just like you remember when we use ant command, there is a build command called ant or maven or say other make. There, if we have multiple, it depends on multiple things and it basically optimizes there. In the same philosophy, of graph evaluation, if you run y and z together, if we evaluate y and z together, in this case, x will be evaluated only once. Okay, so this is an optimization on what we did here. So x will be evaluated here twice in this and here only once. Okay, does it make sense to you? Okay. All right. A question from Minta is there a required structure components to creating and running graphs? Okay, using the TF session. So yes, basically that's what we are discussing right now. All we do is create our expressions. Most of the programs that we have written in past had an expression behind them. So whatever we did, whenever we call the function, we did something, we were basically creating a mathematical expression there, right? So, if we are, let's say here, we are saying tf dot square, right? Let's say we are defining a value called zz equals tf dot, right, square of, say, y plus z, right? And so basically, if you take a look at this, this would be internally, even though it looks like normal calculation that y is x plus 5, z is x plus 3, tf square is y plus z, the whole square. It is essentially a graph that we have built internally. Okay, so that graph is being created internally while you're working in your own way. Okay, while you're working in your own way, the graph is being created internally. Okay, let me just put it separately. Okay, so we could say with tf.session as s. Okay, and we are saying s.run, and let's say we say z, 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 and y. There is no particular order in which you need to call. Anything is okay. Just put them in an array. Okay, and we could actually print the values. All right. Okay, we could just see here the result of say gg underscore v and z underscore v and y underscore v. Don't need to put these. Okay, so good. All right, so you can see that it's 25 square, 10 plus 15 square. All right, so this is what we are doing. Is it clear to everyone so far? So what it did was when we run these expressions like this, it's going to compute these values only once. Okay, because what it'll do is it'll basically optimize that step. Okay, so since right, so here the graph looks like this. So we have what? We have W. I'll just put this way. W was our constant, that is 3. Then we had X and Y. We had X, we had Y, and we had say Z. Okay, so Y was equal to W plus 2, and sorry, X was equals to W plus 2. This okay. All right, and y was equals to X plus 5. Y was equal to X plus 5. Okay, and Z is equal to X plus 3. It actually looks nice. This is how the graph looks like. And then we have, say, okay, so, okay, you can think of ZZ as two operations. Like here we have, say, square operation, right? And say this is, both of these are being added. And then we have this square. Okay, this is how you can visualize it. Okay. All right. So it looks like a transformer. Okay. So we have this kind of a graph. Okay. So this is what we have done so far. Let me just insert this as markdown. That'll be easier and we'll be able to track it. Oh, it's waiting for something. I don't know. Okay. I'll just make it a markdown and then it'll become easier to keep it there. Good. Okay, so I just inserted that. All right, so I hope the graph thing is clear to everyone. So essentially they are computation. These are basically dependency graphs, or you can say DAG, directed acyclic graph, and so on. All right. So using multiple variables in run, we can actually remove the, we can skip the, we can optimize by evaluating the common denominator, common part only once instead of twice. Now, so basically the TensorFlow operations are called ops. Ops can take any number of inputs and produce any number of outputs. For example, addition and multiplication ops each take two inputs and produce one output. Constants and variables take no input and they give out one output. They're called source ops. Specifically, the leaves are source ops. Okay. Now, the inputs and outputs are multidimensional arrays. So here we are just dealing with what? We're just dealing with values so far, only the atomic values, basically the basic 1 to 3 kind of values, the primitives. But most of the time we will be dealing with vectors, okay? And those vectors or multidimensional arrays are called tensors. Okay, that's why the whole name of TensorFlow comes from. The multidimensional arrays are called tensors, just like NumPy arrays. Tensors have types and the shape. Okay, so just like we have NumPy, and the core idea around NumPy is that big array that we create. Similarly, in TensorFlow, the basic primitive type is, as in the one of the core components is that those arrays, the multidimensional arrays. So in Python API, tensors are simply represented as NumPy ND arrays. Tensors typically contain floats, but we can make them to carry strings by using arbitrary binary arrays. Okay. All right. So let's try something interesting. Let's try to utilize our knowledge of whatever we've done so far to do linear regression using TensorFlow. Okay. All right, here's a question for you. So I hope you must be seeing these kind of questions on LinkedIn and everywhere. So we have, okay. So 3 bananas, 5 apple lead to $12. Sorry, 3 apples, 5 bananas is 12. 9 apples, 1 banana is 21. So how much is each apple for, and how much is the banana? Okay, so this is essentially the basics of um, algebra, right? So in the typical cases, in usual cases, what we will do is we will do the elimination method. What we do in the elimination method is we basically eliminate one variable at a time. Let's say we multiply second row by 5 and subtract from first one. Okay, and that way we'll be able to compute the values. Correct? So that's how we generally did. But the problem with this approach, is that if the values are not really precise, okay, let's say this is an approximation, then elimination method does not give you great results. The elimination method does not give you great results. Okay, so that's the basic idea behind using the other techniques than elimination. So how do we generally do it? Using elimination method, we basically eliminate one variable. Let's say we multiply this by 5, right, and eliminate this. Then then we'll be left with only this. So it'll be 9 into 5 minus 3, and this will become 21 into 5 minus 12. So and then we divide from this side. Correct? Let me just, okay, so all right. So let me just draw it somewhere, and okay. So can I here? Okay. Why I'm not able to copy paste? I can delete this. I think this also I can delete. Okay. Okay, so let me just see if I can. Okay, so in here, what we generally do is, let's say we multiply this with 5, right? And then what we'll be left with is something. All right, this will be cancelled and there'll be 45 minus 45 minus 3. uh, Okay, and this side will be 21 into 5 minus 12. And the value of apple is going to be say 21 into 5 minus 12 by 45 minus 3. Is everybody okay with this so far? And then we'll put it back and so on. But this approach is not really great when it comes to approximations, because it assumes that both the equations are perfect. Okay, what if some of the value is truncated here? You'll see that the actually this is an approximation, because if you put the same values in this one, you'll get a slightly different answer. If you put the same values here, you'll get slightly different answer. You basically are not going to get perfect 12 or 21. So the question comes is, in real life, when we are doing any kind of linear regression or anything, it's all about predicting all the values of various coefficient or variables, just like we are computing the cost of apple and bananas, right? So the way we do generally is, we what we do generally is that we assume the value of apple and value of banana. We just assume some value. Then we see how far are we from, say, 12. Okay, how far are we from 12, and how do we compute how far are we from 12, as well as how far are we from 21? How do we compute? By computing the mean square error. Okay, so we will say assume some value for this, some value for this, and compute our output. Similarly, we will do the same thing here. We compute the delta. Okay, and then the next thing what we'll do is, let's say I'll show you something. So let's say we are assuming a value as, say, a cost of okay, cost of say apple is x, 5 5 I'll just put a. Okay, this is the important part. So 5a and equals 12, and say 9a plus 5b equals 21. Now let's say how much the error are we getting? We are getting, let's say here, let's say we are getting this error. Okay, so this is our error. So let's say we assume the value of apple as a, banana as b. The error would be this minus 12, the whole square of it, right? That's how we are defining our error. Okay, so the total error that we would get would be this. Okay, so total error is this. Is it clear to everyone? No? So let's say we assumed a value of apple and banana as say banana as A and B. So the net error is this. Okay. Now question is, what values of A and B would minimize the value of error? What value of A and B would minimize the value of error? How do you do that? Anybody? Okay. This is 3 actually. Okay. Right, right, right. So what we generally do is we compute the partial derivative and equate them to 0. Now, what does it mean by derivative? Okay, this is again a very important concept. We are going to uh, use this again and again. So um, let's say when you are speeding up, or whenever you are traveling, your car's speed is going up and down, right? Let's say this car's speed is up and down. Okay, right? And what do you want to find out? The points where the car was either at maximum speed or at slowest speed, right? So what we'll do is we'll try to find out where where the the curve is flat. So let's say you have a car, and let's say in the beginning, okay, actually the car would be, let's say, over time. Okay, so this is, let's say we are saying time is this side and the speed of car is this side. And let's say we started here, we went up, and then the car's speed became stationary, then started coming down, right? So in this, if we have to find out what was the maximum speed you had, was to basically draw all kinds of tangents onto this curve, all kinds of tangent to this curve, all kinds of tangents are lines touching the curve, right? And all kinds of tangents we will draw on this curve and find out which tangents are horizontal. Okay, is that clear? So the tangents which are horizontal could either belong to the place where the curve had reached its maxima, or the curve was at minima. Is it okay with everyone? This is something we read long back. We kind of forgot it, but it's very, very important. And so that's what we do. Okay. Now, as in, these are the techniques that we use in most of the approximations. And as we go ahead, you will see that we will use that. Okay. So all we do is we draw all possible tangents. Okay. And find out which tangent is horizontal. The tangent could be horizontal in two cases, where the value is either at max or minimum. Okay, and sometimes there could be many points, like more than 10, 15 points, having the value at 0. Okay, those are local minimas. Those are could be local, as in minima or maximum. So basically, we kind of draw the tangents on a curve at every point. Now, question is, how do you generally draw tangents? How do you generally draw tangents? So the way we draw tangents is we take 2 points, right? We take 2 points, say, okay, let me just delete this part. Let's say we take points. Let me zoom it a bit. We take 2 points here. Say this is 1 point, and this is another point. This is a very tiny difference. Okay, and then we so let's say we want to draw a tangent at this point. We go slightly to the left, slightly to the right, and then we draw a line. Then we draw a line. Okay, joining these two dots. Okay, and draw the line, and we compute the slope of this line. How do you so the slope of this line would be, let's say this is this value is how much? This value is, we are computing at x, so let's say this is x minus d, this is x plus d. Okay, we went slightly to the left and slightly to the right. Okay, so these are the two values. Okay, and for each of these values we computed the velocity. Okay, we found out the velocity here. There'll be two velocities here for this and for this. So we say, let's say the value here is, okay, this is v1 and this is v2. Okay, these are two values. So the rate of change of value, that is what is represented by the slope here, is v1, sorry, v2 minus v1 divided by this speed. Okay, this difference. Or if you are able to visualize this particular line, that'll be easier. So let's say there are these 2 points here. There are 2 points here. So we are dividing. This is the y-axis, v1, v2 minus v1, and this is the x-axis. So this triangles. When we divide the vertical component with the horizontal, we get the slope, right? We get the slope. That is what it means by slope. The ratio of vertical component and horizontal, right? So this will be 2D, right? Okay, does it make sense to you? So this is what we call as derivative. So it is derivative of v with respect to, say, x. Okay, here it's basically we call it dx. All right, does it make sense to you? So all we are doing is derivative essentially means find the delta between 2 points in y value, divide by the x value. That is the slope of the line. So the slope of the line is what we call the derivative. Okay, so derivative here will be, because the y component is going to be 0 because it's horizontal, and therefore it is going to be 0. So derivative is the dv by dx in this case, or dy by dx in this case, is essentially the slope of the line. If the slope of the line is 0, that means it is 0. Okay, I hope it was clear. So please feel free to question the approach. So here, um, what we try to describe is that what does it mean by dy by dx? The objective of dy by dx is to find the slope of a curvature, or find the rate of change of one variable with respect to another variable. That is what it is, dy by dx, or derivative of differential, and is basically acceleration. That's right. In case of velocity, we have acceleration, but we could do the same thing with acceleration, and that will be, there would not be any. So change of acceleration with respect to time is called, okay. So yes. So since we don't have names for every change, therefore we generally call it differential. Okay. Okay, good. So basically the points where acceleration is 0 is either when the car is actually stopped, or the car is not accelerating anymore, and hence that is the highest point. Okay, so basically the derivative in case of velocity is acceleration, and the derivative in case of distance is velocity, and so on. So derivative is a general phenomena. The rate of change is basically what we call derivative, right? And there are many uses, or there are many use cases of derivative. One of them is to find out where the value of something is going to be maximum or minimum. Let's say somebody asked me that, hey, can you find out what is the minimum distance? What will it take to reach there? Um, and what is the minimum speed? What is the minimum time that it would take? So all I would do is create an expression for the distance and differentiate it with respect to the time. I'll create the expression for the time, and then we'll differentiate it with respect to time and equate it to 0 and find out the minimum time or maximum time. Okay, that's the general attitude with respect to solving problems. So in the similar way, in case of, let's say, this problem, right, what we are trying to do is we are trying to do approximations, right? So here what we are trying to do is we're trying to do approximation, meaning the guess that we make for apple and banana should have minimum possible error, right? And so how do we define error? We will make some guess, let's say A and B is our guess, right? And we will compute the error from the first one, we square it, and then we'll compute the error from the second one, and we square it, and then we will compute the d of error by d of A and equate it to 0. So rate of change of error with respect to A is 0 at some point. Similarly, the rate of change of error with respect to B would be equal to 0 when when the error is minimum or maximum. Okay, so this is what we are going to do. So here what we are going to do is basically uh, do the differential of this one and equate it to 0. Okay, and so on. And then as a result of it, we will compute what is the value of A, what is the value of B. This is called the normal equation, right? This is called normal equation. This is easier when our expressions are really easy. So we can simply say compute the differential of this expression and equate to 0. It's pretty simple to do that. Okay, but in real life, what happens is these expressions are really complex. Therefore, normal equation doesn't really work well. We can't really compute the differential of everything. Okay, it's difficult to compute the differential of anything. Okay, thank you, Siva, for noting it. So good that you are paying some attention. All right, I think only Siva is paying the attention. All right, good. So any questions at this point? So all we'll do is we compute this differential of this error equated to 0 and so on. So this was the oldest technique of doing the approximations. Now, this technique wasn't useful when the expressions were complex. Here, expressions are easy to compute. Here we say 2 of 3a plus b and so on. That becomes your easier thing, right? So we could just say 2 into this expression. The differential of these one is known as x squared, is known as using chain rules is this. Okay, so into 3, right? So I hope you have not forgotten these parts. So we have we have memorized the differentiation of many expressions, okay, and use something called chain rule to solve most of the differentials. Okay, in the same way, we can compute this as well, and we could say 5 here, and this is 1 here, right? So in these cases, you can see that we will get 2 equations at the end of it, and then you can calculate the value of A and B, right? So this was normal equation. First method was elimination method, right? Elimination method. The second method is the normal equation, right? So these are the two basic methods. The third one is the gradient descent. Okay, so we'll talk about gradient descent soon. Now, so This one was great for the only for the school level, where the most of the problems were kind of concrete. Every answer was perfect, and and uh, basically things were very man-made. Okay, the elimination method works where there is no need of approximation. Okay, but in real world, you need to do a lot of approximation. Okay, you don't really have integers as answers. Therefore, this elimination method never works. So in the real world, what happens is that for apples and bananas, you will have, say, 15 equations, 15 such expressions, or 15 data sets, and 15 data sets, and you will be able to do that. Okay, so you will have to find out the values of this. Okay, so we used to use normal equation. So normal equation here, it looks really complex, right? But if you use a bit of linear algebra, then normal equation is kind of not that complex. Okay, so here is the linear the normal equation way of solving. So what we will do is we will divide. First of all, we'll make this as 1, right? And we represent it like this. Then we will basically represent these equations as this. You see that? So these equations are represented as this left side expression is represented like a giant matrix, right? 1 5 by 3, 1 1 by 9. So this is a way of representing these equations, and there is a dot product between these two. Okay, so dot product is actually designed to solve this kind of scenarios. So you say, you take the first row, multiply it with the column, you take the second row, multiply with the column. Okay, and then you equate it to this side. So this is generally, in case of machine learning, we call it capital X, and these are called thetas. Okay, these are called thetas because those are the things which we are trying to find the value for. We are trying to find these values called thetas. Okay, we're going to approximate these values of thetas. And the right hand side is called small y. Okay, this is theta, this is capital X, this is y, right? Okay, so, all right. Now, theta cap. Okay, theta cap, right? This. Oh, it's not visible here. Strange. The theta cap that we put. Ouch, it doesn't show. Any ideas? All right. So just here, this is called theta cap. Theta cap is optimum value for this. Optimum value for this. And that comes from solving this equation. Remember, the one that we did? This, when you solve that equation, this is the kind of formula that comes out. Okay, the normal equation comes from computing the first differential, equating it to 0, equating the errors to 0 with respect to every variable, every theta. So every value of theta, we differentiate the error and compute it, equate it to 0, and then we find out the values of the thetas. That's what the normal equation is. Okay. So this is basically, in case of scikit-learn, this is the formula that we used. We first computed the x dot t, that is transpose of a matrix. So this x is a matrix. Transpose of x is basically one of the operations on matrix. So we could convert the rows into column into rows. That's what is transpose. And dot product means multiplying row of this one with columns of the second matrix, multiplying rows of rows from first matrix with the columns of each one. Then we have -1 at the top, which is basically the inverse of it. Inverse computation is generally equivalent of using the elimination method. Okay, using the elimination method, the way we computed the eliminated some of the variables and find the values. That whole mechanism is equivalent of finding the inverse, and then we are multiplying again by the xt dot y. Okay, for now it's a little difficult to derive to this equation, but it's easy to actually do the computation. Okay, so using numpy, you can quickly do the inverse like this and dot product like this using dot. Okay, and x dot t means we are computing the transpose of a matrix. Okay, so you can see that here the xt is being computed twice. Okay, xt is being computed twice. So in case of numpy, we'll be computing xt twice, but in case of TensorFlow, since it's a graph computation, xt will be computed only once. Okay, so uh, so LIN ALG is basically it's a linear algebra. You can say linear algebra object, which has methods like inverse and others. Okay, so I hope this is clear to everyone. No? So most of the regression problems are about apples and bananas, right? So, so this is the way we can do using scikit-learn. All right. Okay, so Balaji, Bintao, Gigi, James, Kamal, Shahrukh, Pavan, Ross, and Shiva. So this was the easiest way of, this was the first way of, second way, but the older way of doing the calculation of X and Y. But this was not scalable. This was not scalable because of many reasons. This was only good in cases of when we could do the differential easily. All right. Does it make sense to you? Should I move ahead? So let's try to do that in using first scikit-learn. It's pretty simple. Here I have put the same value. Uh, this is, I have first created capital X, which is numpy array. Okay, we have 1, 5 by 3, 1, 1 by 9. And then we have defined y side. Okay, 12 by 3, 21 by 9. So once we have capital X and small y, what we do is, okay, a question from Binta is, do we must have factors before apples and bananas be 1? Yes. Okay, you will see that because that's what we call bias, and things that we most of the things that we'll see ahead is basically we will add this one extra column mostly in our in our data. Okay, we generally put one extra one. Here we have converted our actual equation into that. Okay, we could also have done it this way, that we put more one here, one plus here, one plus here, and put third variable. Okay, maybe papaya before apples. Okay, so that's another way. Okay, but generally the problem statement is that predict, create the relationship between input and output, and we come up with these variables. Okay, so most of these solutions work well. Most of these solutions work well if the first column is 1. Okay, you will see that soon. So you can see that using the normal equation, first we did this, then this, then this. Okay, to make it further more simple, I'll just try to see if I could say represent this in our, okay, let me just show you here. I think, okay, this is, okay, this is, let's just put comment. So xt equals x dot t, right? And then let's call this whole part as xtx equals xtx equals xt dot dot, okay, capital X, and then I say inverse of xtx equals. So I broke down the entire thing into the into this individual parts. Okay. All right. So that's what it is. And okay, so you can see that. And then we have theta best would be so theta best is the inverse of xtx, right? And then dot xt and dot y. So this is how it's going to be. Okay. I hope this is clear to you that what it means by this expression and this. Okay. So you can see the value of apple is 2.2 and value of banana is 1.1. Okay. 2.2 and 1.1, right? So if you go back here, 2.2 and 1.1, right? So it's not an integer. A question from Binta is, I think we do not need to divide the equation by 3 and 9 respectively. So I have divided it's not really required. It's I've divided to keep it in the same format as we are going to go ahead with our not the other parts. Okay, so we're just keeping it to what we generally do. Okay, keep everything in the same format. Okay, that's the reason. All right, so we were able to use and understand what does it mean by normal equation. Normal equation is nothing but we minimize the error by approximating the values. And how do we minimize? By differentiating it and equating it to 0. So normal equation works well when the data is linear, when we know that there is only a linear relationship, and then normal equation works well. Also, computing the inverse is really hard problem, and therefore it might take a long time. Okay, now we could do the same thing using TensorFlow. Okay, so I think we forgot to take a break. I think we will continue from here. Okay, all right. Please keep asking the questions because that's the way it is going to be clear. Okay. Okay, now the so this time, okay, so let's now we are going to do the same thing using normal equation, but let's use the housing data set. Okay, we will use the housing data set, a more realistic one rather than only these couple of variables. Okay, now in the housing data set, we have multiple columns. Here we were just guessing the value of two parameters. There we have a lot of columns, and every column has got one more theta associated with it that we are trying to guess. Okay, so what we generally do is we are given the input data and output data in case of supervised learning. All we do is we assume that each of the records in the data set, all right, basically is linearly correlated with the output, meaning that if we multiply each column with certain value, we would get the outcome. Okay, we would get the outcome. So okay, that's the idea, and just what values to multiply with is the problem that we try to solve using the regression. Okay, so let's take a look at this problem. Okay, so first of all here, right? So using normal equation, in the normal equation, we generally don't need to put biases, but it's better to keep the data in the same format. Now here, so first of all, we are importing the data set. Okay, we are importing the function that imports the data set. Okay, then we are resetting the graph. Okay, so that our previous works don't mingle with it. Second is we are calling this function that we have imported just now. Okay, calling that function. Next is that we are finding the shape of that function. Okay, we are finding the shape of that function. The shape of that function is basically has number of rows and number of columns, right? And here we are adding the one extra ones to all the rows. Okay, so the sole idea is that whatever is our data, we assume that we uh, we basically think that it is linearly, in this case we are thinking that it is linearly correlated. Okay, so what we are doing is, let's say we have some data from California data. It has first column, second column, third column, and so on, right? And it has some target value. Let's say this is your target, we call generally Y, and then we have X. Okay, so the idea is that for each of the record that we have in this data, for each of the record, we think that there is if we multiply this with certain number, let's say x1, multiply this with x2, and multiply this with x3, and then uh, okay, then so then we'll get the resulting value whatever we are expecting. So the objective generally to find those x1, x2, x3 that optimize, or we also call them weights, that what are those values that we should multiply each row and each column with, such that we get the desired output, right? That is the main thing. Just like we did for apples and banana, similarly we have to find x1, x2, x3. Okay, that's the sole idea behind doing the linear regression. Okay, sure. Now a question is here, right? So this is clear. Next is we are doing this. Okay, let me do one better thing. We will do it stepwise. uh, Generally what you should do is you should actually go expression by expression. Okay, you should go expression by expression just like this. So I'm right now showing you that what does it mean. It means that we want only one, okay, m number of rows and one column. Okay, one column. Now the next thing is, what does it housing.data mean? Housing.data contains what? Okay, housing.data contains this data in this form, right? It has m number of records, and every record has got, let's say, 0. I'm accessing 0. So every row is of this form. Okay, every row of this form. That's housing.data. Now, when we call this, when we call this, what happens? It basically concatenates a column called one, right, with the housing data, right? So it'll put one in front of everything. Okay, so it'll put one in front of everything. Let's say, you can see it has put one in front of the value we were seeking. So in housing.data, if you see housing.data, let's show you what is the first row. So you can see that here there were only these values, and here extra one is added. Same is the case if you take a look at the first row. Same is the case here. This was the first row, and here you can see we have added one more extra ones. So that's what is happening here. So we are concatenating these columns. Okay, concatenating these two these two data sets column wise. Okay, good. All right, so that's what is happening. And next is, now we are defining a constant x. Okay, since the input data set is this, so we are defining that as a constant. Okay, all right. So a question from Bintao is, why add one to each row? Good question. Good question. So we are saying that, let's say, I'll give you a good example. Okay, let's say we are given some data. Okay, let's say we are given two kind of data. That, let's say this one is, let's say we given two data sets. This one is number of visits, right? And sales, right? So number of visitors and sales. So let's say we have to find out a relationship between number of visits and sales. Okay, so we are given some data here. Let's say for 10 visits we had 40 sales. Okay, for 20 visits we had, say, um say how much, let's say 90. Okay, now you can see clearly that if we represent sales, we could say uh, sales equals to some some coefficient, say W. I'll just put W into number of visits, right? Okay, let's say we say this. Is this correct? Yes or no? Answer is no, because it could be of this form as well, right? It could be of this form as well. So it could be such that uh, it is W1 we multiply this with some number and then add some number, correct? That could be the case. For example, here it is 10 into 4 plus 10, right? So here W1 in our this example, W1 is how much? 4, and W2 is how much? 10, correct? Therefore, it's important to add one more extra variable, which we call as bias. Okay, which we call as bias, right? So similarly, so instead of just using this as your capital X, right? What you would do is you will put one more extra column, okay, and say put value of each one as 1, this one as 1, and we'll say that multiply this column with, say, W1 W2, and this one with W1, and find out those values of W1 and W2 which are giving great results equal to what we have here. Okay, so find out those values of W1 and W2 for which we are getting the best results. All right, I hope you got the idea, Binta. Why do we need to add one to each row? Okay, Is everybody on the same page, or have I confused you? All right. Keep asking question because that's what will keep me on the track. Okay. And I'll be, my expectations will be better from the class. Yes. Shiva, Pavan, Kamal, James, Gigi, Binta. Okay. I kind of have a feeling that you all have gone for sleep, or maybe you have gone to do something else. Okay. So please keep on asking the question. Okay. Now, a question from Gigi is that in ML, bias will be automatically added. Um, so you basically will have to add it by yourself because in most of the cases you will be given the data sets, right? You'll be given the data set and will be told that, okay, this is the number of visits and number of sales. Now you find out the out find out the found out the relationship. Now this bias is only needed for some algorithms. Okay, why? Because here we are trying to guess the sales based on linear algebra, and we are thinking that the outcome is the function of input, right? And when we say function of input, it means that we multiply in case of we are thinking that it is linear or something like that. So it could be that it's a square of this, right? It's a square of number of widgets. It's a cube of number of widgets. It's a multiplication of like 4 variables and so on. There could be many situations, right? So the easiest one of them is the linear regression, where we think that the output is a function of input variables multiplied with certain coefficient plus one extra constant. Okay, plus one extra constant. So that extra constant also we need to find out what is that extra constant. So that's the sole idea with linear regression, and that's why we need the bias. So bias is kind of we'll have to add mostly by ourselves. Okay, all right. So and I think the normal scikit-learn fit transform, it adds the bias by itself. I think you are right, Gigi. Thank you for yeah. So I think most of the algorithms fit and transform would add that extra bias internally before doing the calculation. We'll have to see that again. Okay, before we let's say we are using say a dysentery, or we are using say linear regression, so those libraries automatically added bias internally, correct? So here, since we are creating our own formula, then we are using the bias by ourselves. Good, very good point. Very good point. Now moving ahead, so we added a bias. Okay, we added a bias, and we put bias as in we put one, so that the since it's always one, so the w when it's multiplied it's just constant. So it's basically we added extra number. Good, so it's generally 1. Then what we did was we created x, capital X, which is a constant. Notice the constant. We are saying that the housing data, the whole thing, the numpy array, we're creating a constant out of it. Please notice. Now, okay. Now here, you see, what we are saying, we are defining a constant, tf dot constant, and we are passing this data set. Okay. And next thing we are doing here is we're defining second constant here. Okay, why are we reshaping it? Let's just show you what it reshaping means. Reshaping actually converts the data into a single column. Let's just show you what it means. Okay, so the target was an array of single dimension. Then when we reshape it like this, it became a vertical column like this. Okay, vertical column like this. So it's a basically array of arrays, right? Each individual array only is having one element. So this is how we generally define our Y. Okay, so make sure to keep this in mind because this is what most of us make the mistake at. Then we are transposing the x, okay, because that's what is required in the formula. Then we are doing matrix multiplication. This is equivalent of np dot dot. Okay, in np the numpy we did dot product, right? So in this formula where we were doing, so this dot is basically matrix multiplication. This is that. Okay, this dot is the one. Okay, let me just copy paste this one so you'll get a clear picture. So this from here we are essentially emulating this formula. So first we computed the transpose of x, that is xt. Then we did in here again we did matrix multiplication of xt and x, xt and x. Then we did inverse from here to here is equal to this part. Then we did the matrix multiplication of this part and with xt, these two parts. Then next thing is we did multiplication of this and this, that is we multiplied this portion with y. Okay, that's what is happening here. And there we go. So we see that we got the answer. So here these are the various coefficients that should be multiplied with each column to get the desired output with the minimum error. Okay, so we are here again. A question from Inta is, what is the function of constant? Since this data is not going to change during the computation, we are defining it as a constant. So constant can be a vector, can be a primitive value. Okay. All right. Is it clear to everyone? Is it running for everyone? Did you try to run? Okay, great. Great, James. Now, all right. So whatever we did just now, we are going to see the things which are related to it. Like for example, differential calculus. We're going to see more example of the same thing, and at a fundamental level. Okay. All right. Wonderful. So great. We are able to do the housing prediction, right? Write our own kind of the basic algorithm using the normal equation. All right. So this is what we did just now. Okay. Is everybody clear about it? Any questions? Any line that's not clear on this? Okay. Let me just put line numbers so that you can ask about what does it mean by individual things. Okay. So let me just put numbers. All right. Okay. So yes. Any questions at this? Any line number that is confusing to you? So we basically imported NumPy, okay, because we needed to concatenate columns. Then we imported the housing data set, and afterwards we added a bias, one to each column, and then we we defined our capital X, that is the features, and we added a bias to it. Okay. Okay, after loading data, we added a bias and that became our capital X. And then we defined Y by transposing our target variable into one value per row. And then we computed using the normal equation. All right. So great, great. Kamal, all well? Balaji, does it make sense? Great, great. All right, wonderful. Pavan, so yeah, please feel free to ask question if everything, if any of these lines from 1 to 12, any of it is confusing. Okay. All right. So should I move ahead? Great. So what we just did was we created our own solution using we created our own algorithm here, which uses the normal equation. Okay. Or you can say the approximation by the way of minimizing the error. And how did we minimize the error? By equating the differential of error with 0. Okay, and that's how we generally do that. So in this approach, we minimize the error by using the differential calculus. It's not always possible to do that, specifically if your input data is nonlinear. Okay, here it's great for linear. It's great for it's great for great for the cases where the number of features are small. Okay, this does not scale well when the data becomes humongous. Constant is just an attribute of x. That's right. No, so the whole x is actually constant. So we are saying that capital X is a constant value because this is our input data. Uh, it has thousands of records and columns. So since this data is not going to change, these are the list of values. These are the list of values. This data is not going to change. Therefore, 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 we are defining it as constant. All right. Okay. So this is the same. Okay. Okay. So yeah. All right. So good. Was I able to answer your question, Siva? That it's essentially static data, the input variable. Therefore, we are defining it as a constant. And as a general thumb rule, whatever is our input given data, we would define that x and y are generally we define as constant because that is far more efficient. All right. Good. And then we created a session, then we did eval, and there we go. We have the results. All right. Now, let's compare different ways of calculating theta using NumPy and SciPy using the code shown in the book. The main benefit from the previous code versus computing the normal equation using NumPy is that TensorFlow automatically runs on GPU, and if you have GPU, it'll be really fast. The other advantages are not so obvious. Okay, the advantages like computation here, right? So we could actually define xt, right? And so we could actually here in this equation, we could actually make it a little more efficient. And how? We could just the way we realize that xt is being used at two places, right? Xt is being used at two places. So if xt is being used at two places, we could compute it only once and then use it twice, right? And then when we are doing the overall computation, this transpose computation will only happen once. Okay, this is an important aspect. So basically just by taking out this part, we have made it little more efficient. Okay, while in case of non-lazy programming, this is not true. Okay, other than the advantage you will get from GPU, we will get extra advantage like this. right? Why? Because computation of transpose, we have made it faster. We have made it only once instead of twice. Okay, so I hope you are able to see that, right? So out of these two, let's say, let me ask you again, right? So here we are saying transpose, and we are just putting transpose here, and similarly putting transpose here. So you can do you see that here this one is going to be faster than the second one. This one is going to be faster than this one, because transpose here is getting computed twice, while here it's only computed once and used twice. Okay, so other than internally being able to distribute to multiple GPUs, GPU is nothing but bunch of processors bundled together in a single one, that is GPU. And if we are using GPU, that means we are having a huge degree of parallelization. Okay, that means we are having a huge degree of parallelization. Okay, next idea is the third approach. First one was the elimination method. Second one was numerical way of approximation called normal equation. The third approach is gradient descent. Okay, gradient descent is basically an approach where we compute the rate of change. Okay, rate of change of error in every dimension. We compute the rate of change of error in every dimension, and whichever dimension is giving us better slope, meaning the direction in which error is falling better, we move to that direction. So it's an iterative method. Gradient descent is an iterative method. We we start with some point. We start with some point. See if that point is giving better, smaller error or not. Or at every point, we compute the rate of change of error and the direction in which the rate of change is higher. As so the rate of change, how should I say, okay, let me, should I give you a recap of gradient descent, or is it clear? Okay, should I give you a recap of gradient descent, or should I just move ahead? Okay, so let me just give you a, okay, thank you. Thank you, Binta. Okay, so thank you, Shiva, for sharing. Thank you, James, for sharing the documentation. Okay, yeah, I was actually about to do the same thing. Okay, so yes, and good. All right, now coming back to it. So let me show you. Okay, let me just take you back. Right. Okay, I'll just give you briefly an idea the about the gradient descent. Okay, I think that'll help you. Okay, so here we go. Let me just give you a really quick I'll just give you a really quick overview. Okay, without getting lost into too much of content. Okay, All right. So this is the data that we are actually processing right now, right? It has longitude, latitude, and so on. And it has around 2000 districts in the data. So the notations are, the way we keep notations is m is number of instances. So m equals 2000, the number of rows. The xi is the feature values. So each column is basically the ith instance. Sorry, each row is xi. The capital X means the entire thing. Each row is xi. Yi is the label for each row. Okay, so since we are trying to find the median house value, this is yi. Okay, so this is all right. So next is this is basically the xi. Okay, so this is, you can say, x1, and this is y1, right? So capital X is a matrix which has all the rows, right? X1, x2, x3, and so on, and it is basically the entire table, right? H is the hypothesis function, okay, and y hat means the optimum value of y, optimum value of sorry, the predicted value of y. So predicted value of y is the or you can say y hat is equal to the h. Okay, it's also called hypothesis. And yes, so the objective is that we assume some value and assume some hypothesis, then we get the predicted value and then minimize the error. Okay, so you can see that here. All right, so we have the median housing price is this much, the predicted value. If our model is something, then let's say our model is predicting that this is the value, then y hat will be this, the prediction error is this much. So from the actual one, we are subtracting this, and RMSI is the cost function. RMSE is the cost function, which is measured on this set of example using hypothesis. Okay, in general, we will use the lowercase italic font for scalar values, and the bold ones for vectors, and capital ones for matrices. Okay, so that was nomenclature. So here is a very simple mm, example where we have GDP per capita and life satisfaction. So this is where we are saying that if we draw a line that is going through these, the line will have some slope and will have some distance from the origin. That is the bias. You can say theta naught and theta 1. All right. So whenever we are trying to predict a value, we'll have to have two. If we are assuming it to be linear, we'll have to have these two values, right? So I hope this is far more. The visualization makes it very clear, because for each theta 1, there could be many values that are many lines that could go through this. Therefore, we need one more. Okay. All right, so this is what it is. Now moving ahead. So we have talked about this. Okay. All right. Now, this is linear regression. We are saying that the predicted house price is a function of theta 0 added with theta 1 multiplied with first column, theta 2 multiplied with second column. So these are basically, we are saying that let's find out these values which would give us the best prediction. Okay, the objective is to find out these thetas, which will give us the best predicted house price. Okay, that's the sole idea about machine learning, or you can say linear regression. So the y predicted value is equal to theta naught. This is something that we need to find, plus theta 1, that is something we need to find, while x1 is given, x2 is given, and so on. So this is what we want to find out. We want to find out as a result of the all computation. Okay, so we want to find out theta naught and theta 1. Okay, so if we had no bias term, the line will look like this. Otherwise, the line will be like this. Okay. Okay, so general equation of linear regression is this. We say that y hat equals h naught x. Okay, so that's the general equation. And so theta is the model parameter vector, you can say. Okay, so if we are thinking about linear regression, we are saying that the same thing, whatever we have written here, the same thing can also be written like this. We are saying theta transpose multiplied by x, we will get an answer. Okay, so yes, all right. So now, so moving ahead, we have talked about MSE already. Okay, so we're not going to go with that. All right. So let's understand how the training of linear regression model done internally. There are two approaches. One is normal and other is gradient descent. The normal equation, which we have already done, okay, so it has given us some amount of results, and which we have already discussed here. Okay, so normal equation is giving us some amount of results, which is not bad at all. It's actually giving good enough. Okay. All right, now comes moving ahead. Yes. Okay. Now, gradient descent. Again, if we are given some data and we want to find out how is the output related to them, and we think that the data is linearly related, then what we need to do is we need to find out the we need to find out the so coming back again. So if the data is there is a data that is given to us and it is perfect and there are no errors and so on, we could just use the elimination method and find out all the variables. But that's never possible in real world because the data has approximations. It's not exact answer, and therefore we need to use kind of approximation. Now, how do we do approximation? We create something called error, and we find out that we minimize the error by tweaking various parameters. So first way of tweaking was using the normal equation. We basically differentiated error with respect to parameters, equated to 0, computed the parameters. That was normal equation. Okay, second is gradient descent. In gradient descent, what we do is we assume certain values of various coefficients, and at that point we compute the slope, rate of change of error with respect to every parameter. And what we do with that, we basically decrease each of the parameters in the direction where the error is going to be minimum. So this is the strategy that we do. Imagine that you are lost in the mountains in dense fog and you can only feel the slope of the ground under your feet. Which strategy will you take to reach the bottom of the valley quickly? Okay, so let's say this is your current position. You can't see anything, so you can only put your feet forward and see whether it's going down or going up. So basically, what you do is at every point, wherever you're standing, you will find the slope of the slope at that point. So what we do is at every point, wherever we are standing, we find out the slope, and then with respect to that slope, if we start moving in the direction where the slope is going down, okay, the slope is going down. And how do you find the slope? By computing the first derivative, okay? By computing first derivative as in differential dy by dx, okay? So that's what we do in this case. We find the differential, we subtract it from the value, then again try the same thing, and we do it in every direction. Okay, we do it towards the east as well as towards the north. Okay, if we had more dimensions, we will do in all those dimensions parallelly. Okay, if we have say 15 dimensions, we will do that in 15 different dimensions parallelly. Okay, so this is what happens here. So we measure, so the way we do is we measure the local gradients of the cost function with regards to the parameter vector theta. It goes in the direction of descending gradient until the gradient becomes 0. Gradient is nothing but slope. Gradient is essentially dy by dx, the slope, the differential, or you can say derivative, first derivative. So all of that is called gradient. Okay, so we basically compute the gradient, and we start by filling 0 with random values, and we improve gradually, taking one baby step at a time. Each step attempts to decrease the cost function until the algorithm converges to the minimum. Okay, so the learning rate is how big the step are we taking. We multiply that number with each step, and so that is the learning rate. Okay, so if learning rate is too high, then we will, if we are, let's say, here, and we took we were here, we took a really big step. Okay, so instead of like we took a big step from here, we went till here. Okay, so on. Or let's say we were at this starting point, and when we were taking a huge steps, so we might go here, then here, and we'll never converge. So learning rate has to be small, but not too small. Okay, again, in any graph or any data, again, in every data, the cost, sometimes the cost looks really like curve, but sometimes the error, the cost could be having the multiple minimums and minimas. So we have to ensure that we sometimes we kind of get stuck, sometimes we kind of get stuck at maybe here, thinking that there's no slope here going down, therefore I think we have arrived. Okay, so we might get stuck here or here and not here. Therefore, a randomization is required at various points. All right, so this is gradient descent. Gradient descent is all about finding, all about minimizing the error by finding the rate of change of error in all dimensions. Okay, and moving in the direction where the rate of change of error is highest. Okay, so that's what is gradient descent. So that's what we are going to do. So yes, all right. So we are minimizing error by finding in which direction the error is being minimized. Okay, so that's what we do. All right, so where were we with respect to TensorFlow? I think this is where we were. All right, now let's try it. I hope the gradient descent was clear to everyone. Everyone? No? Okay, wonderful. Bintao and James. All right. So now let's try to implement the gradient descent instead of normal equation. So we'll first first manually compute the gradients, then use TensorFlow's autodiff feature, and so on. We'll talk about these few things. These are very interesting parts. All right. So this is what the 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 rate of change of error comes like. So we are saying rate of change of error equals rate of change of error in every dimension. Okay, and that comes out to be this. Okay, so this is our gradient. Okay, this is our gradient. All right, we have x, we have y, and we have this. Okay, so all we need to do is we compute this gradient, gradient means rate of change, means slope of the curve. So this is the slope that will be that will be representing the slope in every dimension. This is in first dimension, this is in second direction. Now on a physical way, when we are standing on a mountain, we only have two dimensions. Okay, we have only two dimensions, x and y, right? And here we have so many dimensions. Okay, so we go in every dimension, such in order to get minimize our error. Okay, in order to find out which direction it is going downhill, and we start moving in that direction. Okay, so next step is going to be previous value minus the learning rate multiplied by the slope. Okay, multiplied by the slope. Okay, so we are decreasing the value of theta, meaning going down. This is the height, this is your height. So we are trying to go down in the direction in which there is a slope. This is the slope. We multiply the slope by a constant factor, and we subtract this value from our current error, current theta. So we take the current theta, find the rate of change of error at this point. If this is negative, that means theta will increase, right? If this is negative, meaning it is uphill, therefore theta will increase, meaning it will go in the direction opposite to it. Okay, so that is the way it is. So basically the this is these two functions, this is how you compute the slope, and this is how you compute the next value or next step. Okay, so this is the way. Here we have put in the same code. Here we have put in the same code. So this is done. Okay, now before going ahead, we are cleaning up data or preparing data. So we scale the data, data bias. Okay, remember that in gradient descent, you should always scale your data. Scaling data means bringing the data to between 0 to 1. Okay, and we are using a standard scaler. We are basically computing how far each record is from the mean, how many standard deviation, and that's how the data will become more regular. Okay, instead of more extreme or more outlier, will become more regular. All right, so that way you can see that we have created the data. We added one extra column, and then we found the mean and so on. Okay, all right. Now the more important part is now computing the gradient. Okay, here is here's the algorithm for gradient descent. Let's start. So first of all, we are defining x. I hope this is clear to everybody. Defining capital X, defining two more variables. Okay, we'll talk about that. Second, we are defining we are defining y after reshaping it to one value per row. Okay. Then we are computing the initial random values of theta. Theta is something that we are supposed to find, but the initial value we are assuming. Initial value we are generating randomly. So we are saying give us n plus 1, give us n plus 1 results to give us these many thetas, and then once we have these thetas, we can do the rest. Afterwards, we are saying matrix multiplication. We are multiply x with theta. Okay. Why are we doing that? Okay, just to get our predictions. Okay. So predictions minus actual is error. Okay. And then, okay, then, right. So we basically computing the mean square error by by squaring the error that we had and so on. Okay, now the question is, what does this particular one mean? Let me just show you. Okay, let me just show you what it means by this. Okay, it computes the mean of elements across the dimensions or the tensors. Okay, so basically, after computing the error, we are computing the mean. Okay, so we took an initial value. We took an initial value of thetas. We did some prediction. We got an error. Then we computed the mean square error, and then we are computing the gradients. Okay, how do you compute the gradient? 2 by m into the dot product of the transpose and the error. Okay, transpose and the error. So let me just show you what it means. So this is it means. So the dot product of the this data, the xb into dot theta minus y. So this is the predicted value. So if you multiply the transpose with predicted value with 2 by m, then you will get the gradients. Okay, so all right. So this is one. Number of epochs is how many times you want to run the iteration. Okay, how many times you want to run the iteration. So here, what we did was we computed the mean error, then we computed the gradients as in the slopes in every direction. How do you compute the slopes? Gradients as in the slopes at every point. Okay, so how do you do that? Okay, by using that formula. Okay, 2 by m, then dot product of the transpose multiplied by error. Okay, now next thing we are doing is we are okay, then we are assigning, we are using tf dot assign, okay, the new value to theta. How? By saying theta minus learning rate into gradients. Theta minus learning rate into gradients. So here, what is it that we're doing is whatever slopes we got, right? We multiplied that with some number and subtracted it from theta. So what we are doing is we found the slope, right? We put our foot forward, found the gradient, the slope, and then we took the next step. We took the next step. This is the next step, which is equal to the current step minus how much slope it is multiplied by our learning rate. Okay, that way, okay, that way we are going to get our training, going to get our next value. So we're going to run these steps again and again, until we get the result. Okay, and please note that here we are defining these steps. Here we are defining these steps. So now we are not running it right now. Okay, at this point also we are just defining an initializer. So then we are creating a session. Here we are creating a session. We are running the initializer. And then these many times, for these many epochs, we are going to execute this part, which is which is evaluating which is evaluating the value of training up. Okay, so this one depends on theta, and theta depends theta is basically a variable, the one that will be assigned again and again, and it depends on, say, gradients depends on capital X is constant, and so on. So you can see that the as and when we are going to evaluate training up, the rest of things will evaluate by itself. Okay, and hence the thetas will keep on getting decreased as and when we are evaluating the training up. Either thetas will increase or decrease, but they will change such that the error is minimized. All right, so this is what is happening here. We are running it so many times. Okay, this is what is defined as number of epochs. Epochs is basically moments, and we are saying run it for so many times. Okay, learning rate, we generally choose kind of a small value. If we choose a high value, it'll keep jumping. So that's how it is. Minus of negative, because gradient, positive gradient means a slope is positive, meaning it's going up, but we want to go down. Therefore, we want to subtract from that. Okay. By default, if let's say slope is already down, that means this will be negative. This will be negative, and hence theta will have to be, next theta will become more value than the previous. Okay. A question from Mita: what are the values for n and m? Okay. So what are the values for n and m? So we had defined it earlier here. Okay. We had defined in that block where we assigned shape to that. So m is number of instances. Here you can see n and m. Okay, let me just take it down because that is causing confusion. Okay, so all right, I'll just put it here. Okay, so this is what it is. All right, so you can see that after some iterations, we are getting this kind of, at 900th MSE, this is what the error is. Okay, this is what the error is. All right, now the interesting part. So here we basically, when we were computing the MSE, we were computing the derivatives, right? And we were lucky to have this kind of form of derivative, because in case of linear algebra, linear regression, where the terms are linear, it's easy to compute the derivative. If the functions are complex, then you can't really compute the derivative. Okay. Now, so is it clear? Is this code clear to everyone? So all we are doing is we have assumed some learning rate, we're going with those so many iterations, then these many records are there, then this is the initial value of thetas that we had assumed using NumPy. Okay, this is NumPy way. Okay, and this is TensorFlow way. Okay, NumPy way would also be clear, right? NumPy way, same thing we are doing here. We are using the same formula to compute the gradients, and then we are decreasing thetas with this formula, doing the descent. Okay, we're computing the gradients and we are doing the descent. Descent means decreasing theta. Initial value of theta is basically the parameters, where we assume some value of parameters. Parameters as in what are the weights, what are the parameters which are depicting the output value. Okay, good. All right. So this was the part where we use TensorFlow in order to compute, in order to do the gradient descent. So we successfully wrote the program using TensorFlow, which does the linear regression used by the gradient descent algorithm. All right. Now let's try a very cool tool from TensorFlow. Now, earlier times, we would always end up computing the differential. Even if you don't know differential, now it is completely okay, because in many cases, it's not required. All right. So when we computed the gradients manually the way we just did, code required mathematically deriving the gradients from the cost function. Okay, the sole idea was we will find the derivative or slopes, but finding the derivatives is a really hard problem. In case of linear regression, mathematically deriving the gradients was really easy, right? It was you can see this is after doing derivatives and things like that, it will basically came out to this, right? That was the gradient descent on linear regression. Okay, now that was very reasonably easy, but doing the same with deep neural networks is quite a headache. If the functions are hard, functions are difficult to represent mathematically, you can't really compute the derivative. There are two sides to it. One, the functions are not differentiable. We are not able to find the differential of it. Second, there are some functions we can't really express like a mathematical formula. Like if you think in any programming language like Python or others, we can't really express everything as a formula. Think of Fibonacci series. You don't know how to represent it mathematically as an expression, as a single expression, right? Therefore, the traditional way, the one that we learned in 12th class in our earlier high school time, the differential calculus, those differential ways are not really efficient or possible in many practical scenario. And the this is where the autodiff comes into play. Okay, let us say we have a function f(xy). It takes two arguments, x and y, and we need its partial derivative with respect to x and y. We want to find how this function changes with respect to y. The rate of change of f with respect to x as well as with respect to y is what we want to do. It could be needed for performing gradient descent or some other optimization algorithm. Okay, so there are four options to find partial derivative. One is symbolic differentiation. Symbolic differentiation is something we did always. And second is numeric differentiation. And how do you do numeric differentiation? Okay, it's very simple. So let's say there was a nice function f, right? Let's say somebody has defined a function f which takes some value and returns does some value and returns some other value, right? Let's say you define this function. Okay, and I want to find out the derivative at x. So what will I do? I will call this function for x plus delta. I'll call this function at x minus delta. Okay, and I will divide it by 2d. Okay, this is what I will do. D being really small, D tending to 0. Okay, so let's say you define a nice function f, has some code in it, and then let's say all it does is what? All it does is it returns x square. Okay, it returns x square. Okay, just imagine that. So f of x plus d will be, say, x is given to us. So I'm finding the derivative at, say, derivative at x equals 100. That's what I want to find. So internally what it'll do is x plus 0.1, right? Minus f of, okay, x minus 0.1, and then it will divided by 0.2. Okay, so here is a simple case. So let me just show you, okay, if it works or not. So let's say we have a function fx and we want to find out this derivative at this point. So this is what we are going to do. So we are defining x as 100, and then we are computing this. Okay, so where did it go? This, right? So the slope as 100 is actually equal to 200, right? This is the slope. This is the slope. This is how much? 200, right? And that's the same as, when we find out the derivative of x square, it's actually 2 into x, which is equal to 2 into 100, which is 200, right? Is it clear to everyone that how did we reach to this? So you can see that even though we did not know what's inside f, we were able to compute the derivative. Yes? Had it been cube, then also it'll give a good result. Okay. Then also we'll get good results, you can see. Okay. So you can see cube is 30,000. 30,000 is 100 square, 100 square into 3. Correct? Which is correct. Is everyone okay with this? All right. So you can see that if you have the values like this, okay, even further smaller, the more smaller you have, the better would be the answers. Okay, so this is a numeric way of doing differential. Yes, this is the second part. Symbolic differentiation is where we have memorized what's the derivative of x squared, what is the derivative of x cubed, what's the derivative of sine x, cos x, and so on. Okay, all right. Bintao, Gigi, James, Shiva, does it make sense to you? I just showed you how to compute derivative without knowing any formula. Okay, so if somebody asks you that, okay, what's a derivative? As long as you know at what point do you compute. This is numeric way of doing differential. All right, so we could do the same thing with gradient descent also, that we basically, instead of applying all kinds of formulas, we just calculate the derivative at that point, and then we will subtract the derivatives after multiplying by learning rate from the various values of theta. Okay, now in the similar way, we have forward mode autodiff and reverse mode autodiff. I think we will cover the meaning of these two probably at a later point of time. Okay, so TensorFlow internally implements reverse mode autodiff. Okay, autodiff is on similar line as what we just did. Okay, it's very similar to what we have normal numeric differentiation. For now, you can think of it this way. Okay, the idea with respect to these three is that without knowing the formula, without knowing what is inside the function that we are trying to differentiate, we should be able to differentiate. Okay, so because problem with manually calculating gradients is, one, they're really hard. Let's say our function is this and we want to compute derivatives, so it becomes like this, and um, that's actually very painful because it's very inefficient, because e to the power x is being called 9 times here. Okay, so it is actually very inefficient. Okay, okay, so basically you will end up having the uh, you'll end up having a lot of manual work in case we are not opting with numerical differentiation. Okay, numerical or autodiff. So TensorFlow's autodiff efficiently and automatically computes the gradient for us and replaces the gradient in the gradient descent code with this. We'll continue from here tomorrow. All right, so we will continue from the automatic differentiation tomorrow. This is the only part that has a bit of maths. Later on, from after this session, the maths will be less, the coding will be more. Okay, it's very important to learn these concepts. because this is very much required. This is very much related to the normal physical life. Okay. And if you have any questions, feel free to reach out to me, because I know that there'll be questions. Or if you there was some part of it that you completely blacked out, as in the completely missed, please feel free to let me know. I will do the recap for you. All right. So thank you, Bintao. Thank you, Gigi. Thank you, James. Thank you, Kamal. Thank you, Shiva. Thank you, Shahrukh. Thank you, Balaji. I look forward to see you tomorrow at the same time. All right.